Okay, imagine for a second that you could take that massive stack of organic chemistry flashcards, you know the one, and just toss it right out the window. No, seriously. What if instead of agonizing over hundreds of completely disconnected reactions, you could tap into the single pulsing heartbeat that drives practically the whole subject? Well, good news, because that heartbeat actually exists. It's all about a world of microscopic electron traffic, and today we are going to learn exactly how to direct it.
If you've ever felt totally overwhelmed by swarms of curved arrows and dizzying reaction mechanisms, you are in exactly the right place. We're going to build a rock-solid mental model around one absolutely crucial concept, the nucleophile. By the end of this, we're basically eliminating the need for rote memorization because we'll intuitively understand exactly how and why these molecules interact the way they do. So here is our game plan for today. First, we'll meet our main character, the electron hunter. 2, we'll pit hunters against bases to clear up some major confusion. 3, we'll figure out what exactly makes them strong. 4, we'll step onto the battlefield of common reactions. And finally, number 5, I'll give you the ultimate reaction checklist.
All right, let's jump right into part 1. Meet the electron hunter. To really wrap our heads around this, we got to stop looking at molecules as just boring letters and sticks on a page. Let's bring them to life. These molecules are active, aggressive characters in a dynamic, microscopic story. They have needs, they have behaviors, and honestly, they are constantly on the hunt. So, by definition, a nucleophile is an electron-rich species that donates an electron pair to form a brand new covalent bond. If you remember your general chemistry, you can simply think of it as a Lewis base. But this is a Lewis base that specifically goes on the attack against electron-deficient targets. It has extra baggage, extra electrons, and it is desperate to share them.
Think of it like a powerful magnet. The word itself is actually a dead giveaway. It comes from 2 Greek roots, nucleo, meaning nucleus, which is of course your positive center, and phil, meaning lover. Put it together, and a nucleophile is literally a nucleus lover. Because positively charged centers naturally attract electrons, our nucleophile is drawn to them magnetically. It just can't help itself.
To make this really stick, let's use a super simple analogy. Picture someone walking into a room carrying a gift. That gift? A pair of electrons. The nucleophile is the person excitedly carrying that gift around. They are the donor, actively seeking out somebody, anybody, to give it to. Now the recipient, the person who desperately needs that gift, is our electrophile. The nucleophile approaches, hands over the electrons, and boom, a new bond is formed.
But how do you actually spot our hunter out in the wild?
Well, nucleophilicity isn't just about having a negative charge, it's really about electron availability. You want to look for atoms like oxygen, nitrogen, or sulfur that are carrying lone pairs of electrons, or maybe double bonds loaded with pi electrons. You'll definitely often see them rocking a negative charge, like a hydroxide ion or a chloride ion, but they might also just feature areas of really high electron density, like a bulky aromatic ring. Basically, if it's hoarding electrons, you've probably found your hunter.
Moving on to part 2, hunters versus bases.
Okay, we need to address a massive pain point for pretty much anyone studying organic chemistry. It's a classic case of mistaken identity, confusing a nucleophile with a base. It helps to think of this as a split personality scenario for certain molecules. The entire distinction comes down to what the molecule decides to attack in that specific moment. If our electron-rich species goes after an electrophilic carbon to form a brand new bond, it's playing the role of a nucleophile, usually in a substitution or addition reaction. But if it decides to attack a simple proton, an H+, just to strip it away, then it's playing the role of a base in an acid-base or elimination reaction. Same molecule, totally different agenda.
And seeing a hydroxide ion in action is such a brilliant illustration of that split personality. In one scenario, the OH- spots a slightly positive carbon, swoops in, forms a new bond, and bam, it's acting as a nucleophile. But in a totally different scenario, that exact same OH- ion just reaches out and plucks a proton right off an alcohol, acting strictly as a base to form water. The molecule itself didn't change one bit. Its target changed based on the environment it was dropped into.
All right, part 3. What makes them strong?
So, if these molecules are out prowling for targets, what makes some of them absolute apex predators while others are, well, kind of weak? This brings us to the variables of nucleophilicity, which is basically a measure of how aggressively a species attacks a carbon. We have 4 main structural variables to look at. First, charge. A negative charge is always going to make a stronger nucleophile than its neutral counterpart. Second, electronegativity. An atom that is less electronegative holds its electrons a bit more loosely, making it a way better, more willing donor. Third, steric hindrance. Big, chunky, bulky nucleophiles get physically blocked from their targets, which makes them much weaker. And fourth, resonance. If a molecule's electrons are delocalized, spread out across the molecule, they just aren't as available to attack, completely sapping their strength.
But here's the catch. It is not just about the molecule itself. The environment plays a huge role. The type of solvent you use completely changes the game. If you're in a polar protic solvent like water, hydrogen bonding essentially builds a physical cage around small nucleophiles, bogging them down. In that kind of environment, larger ions actually perform better because they don't get trapped as easily. But swap that for a polar aprotic solvent like acetone, where there's 0 hydrogen bonding, suddenly those small ions are totally free, highly reactive, and the whole order of strength flips upside down. The environment literally dictates the speed of the hunt.
To really build your mechanistic intuition, you have to get inside the head of the hunter. When they scan a molecule, they are hunting for electron-poor targets, specifically carbons with a partial positive charge. Think about an exposed carbonyl group. Because oxygen is incredibly electronegative, it selfishly hogs the electron density, pulling it away from the carbon. That leaves the poor carbon totally exposed, partially positive, and highly electrophilic. I mean, it is absolutely the perfect target for a nucleophile to strike.
Which brings us to part 4, the battlefield of common reactions. Now that we know who our characters are, what their strengths are, and exactly what they're hunting for, let's step on to the actual battlefield. Let's see these hunters drive some real chemical reactions. Nucleophiles are the primary engines behind 3 major reaction categories. You've got substitution reactions, your SN1s and SN2s, where the nucleophile aggressively swaps places with a leaving group. You've got addition reactions, where the nucleophile attacks that exposed carbonyl carbon we were just looking at. And you've got elimination reactions, E1 and E2, where our species decides to play the base, steals a proton, and forms a double bond. Let's zoom in on the absolute classic, the SN2 substitution.
The SN2 mechanism is basically a lightning-fast, concerted, one-step ambush. Imagine our target carbon is just minding its own business, holding hands with a bromine atom. In step 1, our nucleophile, let's say it's OH- again, sneaks up perfectly from the backside, exactly 180 degrees away from that bulky bromine. In steps 2 and 3, it launches its attack, creating this incredibly brief, high-energy transition state, where the carbon is temporarily attached to 5 different things at once. Finally, the bromine, our leaving group, just gives up and departs with its electrons. The wildest part? The carbon center physically inverts. It literally snaps backward like an umbrella catching a huge gust of wind. Chemists actually call this specific flip a Walden inversion.
And what's really cool is when you anchor those 4 steps directly to the curved arrows, you can map the exact trajectory. You see the arrow of the nucleophile initiating that perfect backside attack. Then you see that crowded, chaotic transition state where bonds are forming and breaking at the exact same time. And finally, the dust settles, leaving you with a perfectly inverted product and a detached leaving group. It is just one fluid, beautiful motion of electron traffic.
Let's wrap this up with part 5, the ultimate reaction checklist.
We have covered a ton of ground here, from the basic definitions right down to the deep mechanistic steps. But how do you actually use this when you're sweating over a blank exam paper? You need a tangible tool.
So whenever you face a reaction problem, systematically evaluate your hunter and your target. Step 1. Identify the nucleophile. Is it strongly anionic, or is it neutral and weak? Step 2. Check for resonance. Are its electrons ready to strike, or are they trapped in a stabilized structure? Step 3. Evaluate the carbon target. Is it partially positive and screaming for electrons, or is it hiding behind a wall of bulky sterically hindering groups? And step 4. Assess the leaving group. Is there a partner on the target molecule that's actually willing to pack up and leave when the attack happens?
Moving right along the checklist to Step 5. Based on how you answered the first 4, you choose your likely mechanism: SN1, SN2, E1, or E2. Step 6 is absolutely critical. Do not rush this. Map out the curved arrows directly from the nucleophile to the target. I promise you, physically drawing the arrows prevents so many careless mistakes. Step 7. Double-check your final product structure and make sure your formal charges actually balance. And finally, Step 8. Draw out the final picture.
Bringing this all together, I want you to remember that, especially with tricky molecules like carbanions that have resonance, you always have to visualize the final picture where the negative charge lives in its most stable location. Because that most stable state, that is the part of the molecule that actually does the attacking. If you can memorize that one concept, the reactivity of organic chemistry will finally click into place.
Look, if you remember literally only one thing from this entire explainer, please make it this golden rule. Nucleophiles donate electrons, electrophiles accept electrons. Every single bond-forming step in organic chemistry boils down to this one beautiful principle: an arrow loaded with electrons, desperately seeking a target.
You now have the mechanistic intuition to look at what seems like a totally chaotic jumble of atoms and instantly see the story unfolding. You know exactly who the hunter is, you know what target they seek, and you know how the environment changes the rules of the game. So I'll need you with this thought to chew on. If you can master predicting the flow of something as invisible as electrons simply by identifying the hunter and the target, what other incredibly complex, intimidating systems in your studies, or even in the real world, could you completely demystify using this exact same mindset? Keep asking those questions, keep looking for the underlying flow, and I'll catch you in the next explainer.